sometimes the most obvious things are the things we forget. You know, that's what stereo is. It's not simply left and right and something in your face. It's actually a whole three-dimensional experience. And if you want to hear that properly, you have to record it properly, you have to do everything in your processing in the right way. And in order to do that, you have to be able to hear what you're doing. And your stereo speaker system, plus its acoustic environment, has to be able to represent that in space. And so many times that doesn't happen, because for lots of different reasons, which I'll go through. But that's just a good introduction to the egg, basically, because that's exactly what we're trying to do. We're trying to create a stereo system that truly retains, if there is any, the three-dimensional information that actually comes out of a stereo recording. It's not simply a one-dimensional left and right. It's actually got depth, it's got perspective, it's got all kinds of artifacts that the ear and the brain are quite capable of resolving and synthesizing, but they have to have the basic information intact in the first place. If you don't have it intact, you can't create these effects. Okay, and what we tried to do together, Munro Acoustics and SE Electronics, is actually approach the project purely from that point of view. How do we make the system so completely accurate that you can actually hear all of these effects that are quite often missing, quite often buried in the reproduction technology? Okay, so first of all, what is a monitor system? Okay, I'm going to go through that piece by piece. I'm not going to elaborate right now. The reason why we use an egg, I'll explain. Why do speakers all sound different? Well, I'll give some idea about that. But most small speakers do sound different. You could line up 10 different monitor systems, and they all sound different to some extent, including the egg. But what we're trying to do with the egg is to remove the coloration, the artificial effects that come out of a loudspeaker. What we're trying to do is create something that just is as natural as it possibly can be. And that, in our opinion, is what perfect sound should be. And can a small speaker deliver? Well, yes, it can. In fact, a small speaker can do it more easily and better than a big speaker, actually. Big speakers make things worse, not better. All they succeed in doing is making things louder, basically. What about the room? Very important, as I'll show you. The acoustics are very important. And at the end, what price perfection? That's for James to answer. Okay, so when we started this project, we had to have the conceptual shape. And I'll show you a slide in a minute which explains why we chose this shape. It's basically to avoid any corners. And the idea basically is that the sound can radiate as a sphere, as an infinite baffle, a truly infinite baffle, where there's no beginning, no end. The sound simply wraps around the speaker. And that removes diffraction, discontinuities in the frequency response, and I'll show some examples of that and explain it in a second. But the alternative to using this kind of shape basically is an infinite baffle, which is actually a plane. If you imagine the speaker mounted in a wall with an infinite boundary, then that would actually be a true infinite baffle. But that's rather impractical to build, especially in a small room. So this is the next best alternative, basically, in terms of achieving what, in effect, is a dimensionless boundary. So then we come on to this idea of zero discontinuity. The whole idea basically is that there's no sudden change in the radiation baffle of the speaker. And the only way you can do that is with a smooth curved surface. There is no other way of doing it that I know of. One very important addition to that is reducing the size of the drivers, because as a driver gets larger, it actually creates its own baffle. And one side of the speaker can be actually out of phase with the other side of the speaker as it's radiating. So it's very important to reduce the size of the drivers to maintain this zero discontinuity effect. The other thing to do basically is to reduce your crossover frequencies as much as possible. The lower the crossover frequency, then the less chance the driver has to become directional. That's a quite important aspect of reducing the coloration and the distortion of the system. And that tends to optimize the phase response, because the lower the crossover frequency, generally speaking, the less likely you are to have phase discontinuity from going from one driver to the next through the spectrum. And then the end result of that basically is a smoother frequency response and more even room distribution. That means the speaker's radiating the same spectrum in all directions. A lot of speakers measure very flat and accurate on axis, but off axis they can be completely wrong, and that means the energy in the room isn't the same as the energy coming out of the speaker, and there's an imbalance in the sound, which is basically the power distribution of the speaker, the acoustic power. And all of that basically goes together to produce low coloration. And I'll explain all of these terms as we go along. This is the original research that was done by Olson in America, which shows the effect of the shape of the loudspeaker on the frequency response of the loudspeaker. And you can see that the traditional shapes, like these box shapes here, have very big discontinuities in the frequency response. This is measuring on axis of the speaker. And it's exactly the same drive unit in all of these boxes. Okay, so the only difference is the box shape. And you can see that the spherical shape has no discontinuity at all.
Oh, that's cool.
It's completely smooth.
I haven't seen this before. That's really good.
Yeah.
Put that on the brochure, you know.
And they've all got sort of varying degrees of distortion of the waveform. And it's caused by the sound literally falling off the edge of the box. At every half wavelength you get this sort of discontinuity effect. But when you've got a dimension of the baffle which is coincident with the actual wavelength of the sound, you get a big discontinuity. And that's why you get such big variations in the frequency response. So that basically was the starting point. We knew that in theory the continuous curved shape was the best way to do it. We just had to figure out how to actually build it. And this is where SE Electronics came in. We designed the basic concept of this, and then the factory in Shanghai actually spoke to some various moulding manufacturers and worked out the best way to actually construct a spherical loudspeaker, or an egg-shaped loudspeaker in this case. The reason it's egg-shaped is quite obvious when you look at it like this. You've got to be able to put the drive units into the egg. So you have to have a flat surface on the actual radiation front here. But what we tried to do was smooth out the transition as much as we possibly could and make it as close to a true curve, as true sphere as we could. You can see a lot of things in the construction here, the webbing and the way it's made. Basically, the whole idea of this is to remove all of the resonances in the sphere construction itself. And you always have resonances in a material. Any material has resonance. It's just part of physics. But if you reduce the thickness of the cabinet and you increase the stiffness and you optimize the modulus of elasticity, I shouldn't have had that warning, should I? The stiffness of the box. Okay, if you get all of those things right, then the resonant frequency is very high. And if you can get it above the crossover frequency, then there's nothing in the bass driver that can activate the resonances of the material itself because they're too high. And the tweeter doesn't really activate them because the tweeter's a closed device. So it's only radiating on the outside of the box, not the inside. Okay, so you have a resonant frequency, but it's too high to actually be excited by the... do you want to switch that off,
I'm
James?
just about to, sorry.
And the net result is no resonances, basically. We've measured this with accelerometers on the outside of the sphere, and it just doesn't produce any significant resonances at all. You can feel a slight tingling when you touch the box, when you touch the egg, but it's of no great consequence because it's high enough to be... it's not re-radiating, or nothing we've been able to measure has been shown as re-radiated energy. So that's the whole idea of it.
For that?
Basically. Sorry?
What's the material you're using for the shell?
It's a resin impregnated plastic, basically, very, very hard plastic. But it's got a Young's modulus of 50 times 10 to the 9th.
Okay.
Not many people know that. Which is about the same as glass, actually.
Yeah.
It's very similar to glass, really similar. And you could make a speaker like this out of glass if you could actually find a way of doing it. It wouldn't be a bad exercise to try. But from a manufacturing point of view, this is a lot easier. So it's been quite scientifically thought out. And then you can see the two faces there, the front and the back. And then there's a small curved back panel as well, which goes on. So it's actually made in 3 pieces. And the base port is moulded into the front panel there. And that's got slightly curved edges there, which you can just about see, which reduces another thing to do with diffraction of energy coming out of the base port. Okay, so just talking a little bit about this idea of radiation. There's a lot of thought about near-field monitoring, and once you're in the near-field so-called, you don't have any influence from the room. But you can see that at a distance of 1 metre from the loudspeaker, you've got a wavefront which is actually 13 square metres, which is 4 pi r squared. And your ear has an area, or two ears have an area of about 0.04 square meters, something like that, which means that only 0.01% of the energy radiated by this loudspeaker at low frequencies goes directly to your ear, which means 99.99% of the energy is actually going into the room. And you can't get rid of all of that, so some of it's going to come back and hit you. And that's why at low frequencies, even at a distance of 1 meter, the room has a very big influence on what you hear. And you can measure that very easily with all near-field monitors. You can actually hear and see the anomalies in the frequency response. So it's very, very important to put the speaker into the right kind of environment, any loudspeaker. But you can see now why it's worth actually making the rest of the sound actually radiate in a similar sort of pattern, because if you have this sort of radiation at low frequencies, which you can't avoid, you'll get that from any loudspeaker, then if you don't match it with the low mids and the main mid-frequency information, at least to some extent, then you're going to get this imbalance in the sound, because what's coming back to your ears from the room is not complete. It's only got the low frequencies, not the mid or high frequency.
Not what to say about that one, is there?
How did that one get in there? Okay. This is just a way of illustrating that, basically. If you take the direct sound, just to explain, this is distance along here. Imagine a loudspeaker at 0.0. So this is the distance in meters away from the loudspeaker. And this is a logarithmic scale in decibels. So the direct sound decays like this, which is called the inverse square law. Every time you double the distance, the sound level drops by 6 dB. Okay? And then you've got the room sound, which is all the energy that's bouncing around the room, which in theory, and I say in theory, is a constant. So no matter where you go in the room, in theory that room energy would stay constant, which isn't actually true, but you've got to start somewhere in terms of theoretical analysis. Now the combination of the two is actually what you hear. The purple line there is actually what you actually hear at your ear. And it's a combination of the direct sound and the indirect sound. Now the point where those two are equal is called the critical distance. Okay? And that varies according to the reverb time, because if the reverb time is short, then that level drops. If the reverb time's longer, a lively room, then that goes up. Or more often in low frequencies it goes up, because the reverb time's usually longer at low frequencies. So that's a variable, but the direct sound's a variable too, because depending on how directional the loudspeaker is, you can actually change the rate of change of that. You can't change the inverse square law. It'll always be 6 dB per doubling of distance, but you can actually change the rate of it in relation to the energy levels. So that point there, in a way, is one of the best places to listen if you want to balance sound, because you're getting the direct sound and the room sound in equal measure, and to some extent that's true. But if you're listening in the near field, which is up here, then you'll hear predominantly the direct energy. But that all changes at low frequencies. As I say, as that reverb time goes up, the direct sound, the near field zone, if you like, gets smaller. This is the reason why we use small bass drivers. The bigger the bass driver in relation to the wavelength of the sound, the bigger the difference you get from one side of the driver to the other. So if you measure on axis, you get a good summing of the sound, but as soon as you go off axis, you start getting these lobing effects where the sound actually cancels, because the sound from one side is out of phase with the sound from the other side. So you get this very pronounced lobing, and that's another reason why the energy radiating into the room doesn't work very well. It's not just the shape of the cabinet, and it's not just the way the sound radiates off the baffle of the cabinet, it's the actual drivers themselves that to some extent determine this directivity.
Get this out of your way.
Yeah, that's kind of that's tripped me over. So all of these things conspire together to make what's called coloration, basically. And that's a sort of an idealized polar plot for a loudspeaker where you've got omnidirectional sound in the low frequencies, but it's still fairly even and well distributed in the mid and high frequencies, mid frequencies, and then it's only when you get to the very high frequencies that it actually becomes much more directional. That's when you get up to above about 5 kilohertz. And once it's above 5 kilohertz, then the speaker becomes directional whether you like it or not. It's just a question of how directional. And the smaller the driver, the less directional. It's as simple as that. Okay, but that's a good example of a well-distributed polar response. And if you choose the wrong drivers and you put them together in the wrong way, then instead of getting that, you'll get these great big holes and lobing effects, and that affects what you hear back from the room. Okay, so to define a near field properly, basically it's defined as at any given frequency a distance of less than 2 wavelengths. Okay, which means you'd have a critical distance of 1 meter at 688 hertz, and at 1 kilohertz the critical distance is 0.688 meters. That means basically even at 1 kilohertz you have to be closer to the speaker than 0.688 meters to be in the true near field. Okay. Most people are listening to near fields at about 1 meter. So basically anything below 688 hertz is going to be in the reverberant sound field. That's another way of looking at it. You can look at it either in distance or frequency, or one is the inverse of the other. Okay. So what I'm saying basically is that at low frequencies, or even low mid frequencies, you're not actually in the near field. You're actually in the combined near field, far field response. And that's why we hear things differently with different loudspeakers. This is just a little bit of history. We've known about these sort of effects for quite some years, and this is a speaker system I designed with Dyne audio drivers, in fact, many years ago. It was actually, ironically, it was for a Neve console, but a previous generation of Neve console, the 88R console. And this was actually the launch of the 88R console in Los Angeles, which we did with a 5.1 monitoring system. But it shows you we're just beginning to sort of get into this idea of discontinuous baffles. It's not a very good example because it's still got a flat front, but at least it shows we were sort of aiming in that direction to try and get a slightly different shape to the loudspeaker. Okay, coming back to the egg then, we've decided on the optimum size of the drivers for the reasons I've explained. So now we've just got to design the electrical response. And this shows you basically the typical range of amplification required to match the drivers. Now, the tweeter's more sensitive than the woofer, okay, which is the case with most drivers, so we don't need so much electrical power for the high frequencies, okay, so that's the contour of the high frequencies, and that's the contour for the low frequencies, with just a little bit of adjustment here in the mid-range, which is this optimum hard, soft sound that you've already heard downstairs. And this is the range of equalization on the bass amplifier, which is available on trim pots on the back. And have you seen the back of the actual control unit yet? Mm-hmm. Okay. So that's the level of adjustment that you've got, if you like, on the low frequency amplifier. And that's the range of adjustment on the high frequency amplifier. So you've got quite a lot of electrical adjustment there. It's not EQ well, it is EQ. It's changing the response of the amplifier to match the drivers. But put the two together and you end up with the correct response, which is that basically. And this is an actual in-room measurement, so it shows you that you've got a very, very smooth frequency response. And this was the early attempt basically at this mid-band EQ. And what we were trying to do basically was at a maximum try and match the response of an NS10, and at a minimum have a more or less hi-fi, sort of slightly smiley response. But that was quite an early attempt, and that's not actually the way it is right now. It's not far off that, but what you'll see in a minute is a smoother version of that. And you can see here the bass tuning is quite precise. It actually rolls off quite neatly in the bottom end. Now this is an interesting one. This is a measurement very, very close to the bass driver and the bass port. It's actually a point between the two, just a few millimeters from the cabinet, but actually between the bass port and the main driver. And you can see that there's virtually no difference in the response. This is 1 dB per division. Okay, so there's less than 1 dB variation in the actual radiated output of the speaker from, that's 98765, so from 50 hertz to 500 hertz, there's less than 1 dB variation in the actual radiated power of the loudspeaker. Okay, and that's the best I've ever measured on any speaker, ever. And that's not a tweaked result. I could go downstairs and do exactly the same measurement today. Okay, it's a true measurement. And it just shows you just how accurate the tuning is between the bass driver and the port, and the fact that the cabinet's not influencing it in any way. Because if the cabinet was creating a lot of impedance, acoustic impedance discontinuities, you wouldn't be able to get that. You just wouldn't be able to get anywhere near a response as smooth as that. Okay, this is actually a measurement downstairs in the room, and you can see how sharp that bass cutoff is. It's a very well tuned low frequency response. And then you've got the usual sort of in the room effects here, which you can't get rid of. You can't have a perfectly flat response in a room. It's just not possible. And you can EQ all that sort of stuff if you want, but that's a completely unequalized. Just what you see is what you get response. Okay, that's the impulse response, which looks fairly typical for a two-way speaker. Except to say the bass is very well damped. So on a lot of speakers, when you measure them on the impulse response, you'll see that the bass sort of goes down like that and then up again and does that for a while, for a few milliseconds. But this one's very, very short in its low frequency impulse response, which is the way it sounds. It sounds very, very tight. And that's the phase response through the crossover. Again, there's some variation. You can't get a perfectly flat phase response out of this sort of speaker. You just can't. You can by electronically processing it, and you can use DSP and you can use FIR filters and that sort of thing. But this is a totally analog system, okay? And that was one of our very first decisions. We wouldn't have any digital processing in this speaker, not even in the power supply. So we've got a nicely smooth response across the crossover. There's about 30 or 40 degrees of phase shift over the whole of the mid-range region. But it's a very smooth transition. There's no sudden change of phase, which is more destructive. And the net result of all that is that top curve there is the reference response, which I do at 0.5 meter. That's my standard measuring distance, and it's mainly to get rid of as many room effects as possible. It's not an anechoic measurement, it's just a very close-up measurement. And this is the in-room response. And I took both of these measurements downstairs, okay? And you can see that they're virtually identical. There's a few ripples here. But the thing is, this was taken at 0.5 meter, this was taken at 1.5 meters. Okay? So, the point is they're almost identical, which means that the energy coming into the room and combining and coming back into the speaker, together with the direct sound, is almost identical. So you've got this perfect balance between the two. And that's the impulse response of the top curve, the reference one at 0.5 meter, and there's the left and right. I can get the microphone in exactly the right position so you can see two impulses there, but you can see from the shape that they're identical, basically. Sorry. This, just by comparison, is the Yamaha NS10, and this is the reason why we tried to do that EQ curve the way we did it, because people use this speaker and it's kind of a reference speaker, so we thought, okay, let's see what that does. And you can see, this is a true response, okay? This is measured in a laboratory. And you can see the difference between 50 Hertz, 75, 95. So there's 20 dB's difference between 50 Hertz and 1.5 kilohertz. And that's a reference speaker, they say. But this is what gives the NS10 its unique sound, this sort of mid-range peak. It brings the vocals out, and it's actually quite useful in a way when you're mixing to actually be able to hear your vocals very clearly when you're soloing them. So it does have its uses, but as a mastering speaker and a mixing speaker, I think it's very very questionable. This is testing the eggs. This is a studio in London that we designed, Sphere Studios, and that has a very big custom-built system which we made, and we were comparing the sound of the Sphere speakers with the big system. And the sound was, in balance terms, was very, very similar. Very, very similar indeed. Obviously, the big system can be much louder, no question. But
Sorry about that.
okay,
Don't worry.
no damage, no damage.
You can't finish those.
But the point is, this system costs about €50,000, and this system doesn't. But the sound was virtually identical, actually. At low levels, obviously. And this goes down a little bit lower in the bass frequencies. It goes down about another 10 hertz or so. But unless there's something down there to hear, you don't hear it. So normally the sound balance is almost identical. And that's a very important thing. So one of the biggest problems we have in big commercial studios is you've got the near fields and the main monitors, and you switch from one to the other, and they're totally different. So nobody quite knows what's right or wrong. But with this system and this one as well, you can switch between the two, and it's virtually identical. And that's in my opinion, a very good step forward in terms of the way things should be monitored. And that's the same setup downstairs. That's the same console as downstairs, but obviously they've built a slightly better console since I was here last. So cleared up some of the mess. But nearly all the measurements that I just showed you were made in this room with that kind of setup there. So I haven't used any special tricks or anything. It's just absolutely a normal room. And this is the way we designed that room downstairs. The original room had a reverb time that was quite extreme. It was up to 2.5 seconds in the at 250 hertz. So we used the Baffle panels that SE Electronics already had, and that smoothed out the response quite nicely until you got down to the low frequencies, and it's still nearly 1 second at low frequencies. So I designed those 4 big boxes that you can see on the wall. And that brought the reverb time down to 0.6 at 63, which is about right for a listening room.
Are they tuned boxes though?
Yeah, they're tuned to 63 hertz. And it's about 1.5 octaves bandwidth, something like that. It's a standard BBC box, basically.
Excuse me, Andy, I've just got to make a call. So
Yeah,
you
yeah.
can shout when you need me.
Yeah, sure, okay. But in a way that shows you how, relatively speaking, it's quite easy to design a listening room if you've got measuring equipment and you know more or less what to do. I mean, it only took about 2 days of actually measuring and tuning to get this room right, and to go from that to that, you know, it wasn't that difficult. So I get quite annoyed when people have rooms that just don't sound right, because it's not that difficult to do it. But so many people don't, and they just use bits of foam, and they put speakers in the wrong places, and they do all kinds of things really that are not that difficult to correct. But time and time again, people don't do it. So it's up to you guys to tell them, yeah, just listen and use your ears, and then do something about it. There you go. So basically, I think we've basically achieved a step forward in terms of monitor design. Less distortion, more headroom, relatively speaking. It's not the loudest speaker in the world, but at least it's got true dynamic range over the limits that it does have. And it's totally analog, right? I've got nothing against digital processing as such, but in the right context. If you've got digital sound and you need to manipulate it or something, that's fine. But when you're listening to it, it's an analog experience. And I think the monitor system should be analog, basically. I think as soon as you start introducing digital tricks into your monitor system, then there's always a slight question mark about what's actually going on, whether it's truly what you're hearing or what the speaker's making you hear. And I do believe that. And basically, everything that I've done is not rocket science. It's all been done before by various people at various times, but it's just putting it all together into one package and making it work. And that's taking the time to do it. 2 years it's taken to design the speaker and build it and put it into production and get it here. It's a long time, and most people don't take anything like that time. And you've seen the result, so there you go.